Hey everybody, welcome back here. We are branching off into another unit here and we're taking a turn. We're going from small scale and we're kind of building up to the large scale now. So previously, right, we've been talking about atoms and molecules and we're kind of stuck there, historically speaking, until the 19th century here. I just had to remind myself. So we're going to talk about this, okay? And we're going to talk about a unit that is very important in chemistry called the mole. I want you thinking for a second, what makes it difficult to know how much of something you possess or make or use? And by something, right, we're talking about molecules. So if I came up to you and I was like, all right, how many water molecules exactly do you have in your water bottle? Do you think you could tell me right away? And most people are going to be like, no, you're crazy, Mr. Brester. Like, that's way too many molecules. I don't know. The thing is that there is a conversion that we can do called a mole conversion, and we can actually figure out in any object exactly how many atoms or exactly how many molecules there are in something. And that's what we're going to practice this week and next week for a little bit. And probably Friday, in addition to your homework that I'm going to give you for tomorrow, which is going to be Wednesday, Friday I think we will practice some of you at home figuring out how many atoms you have in things that you have at home, which I think might be a little fun. So we're doing 7.1, mole conversions, which is focusing on converting between atoms, mass in grams, and then moles. And now you're probably wondering, right, what is a mole? Because you're like, it's not the fuzzy little thing, because we're talking about chemistry, obviously. So if you haven't heard of it before, it's this unit that we came up with. As scientists realized that it would be helpful to understand how many of something that we have, this scientist, Emilio Avogadro, came along and he theorized that under the same pressure and temperature and volume of any gases, let's say you kept them in two identical jars, right? You have a jar of oxygen gas and a jar of hydrogen gas. Avogadro said as long as those jars were the same volume, so we could say a liter. They were both a liter, they were both at 27 degrees, and they were both at 1 atmosphere of pressure. They should have the same number of particles. There should be just as many oxygen atoms as there are hydrogen atoms in the other tank. And he was proven correct. Okay? As long as all of the same conditions are met, those ideal gases have the same number of particles. And so he based his unit off of that, and it's called the mole. And now we use it all the time for basically any measurement any chemist ever makes. It revolves around the mole because it takes our numbers on the atomic and molecular scale and moves them into the macro scale, right? Something that you can touch and hold that is kind of more life-size for us as humans. So the mole is just a unit of measurement that specifies a number of something. And that something can be anything. And this is the part that's a little difficult for people to comprehend at first. Okay, 1 mole is equal to 6.022 times 10 to the 23rd of anything. And when we see the mole written out, it's going to be MOL, like this, okay? Mole. We take off the E. If you remember back to our SI units, okay, we spell it out MOLE. But here, when we write it out as a unit, it's MOL. So we finally reach back to the mole. My example here, 1 mole of ducks. Okay, that's just 6.022 times 10 to the 23rd ducks. This is 1 mole, 6.022 times 10 to the 23rd number of whatever unit. So if we're talking about ducks, it's ducks. You can kind of think of this like a dozen eggs, right? 1 dozen is always 12 of something. Usually it's eggs, but I could have a dozen donuts, or I could own a dozen cars if I was not a teacher and had more money. You could have 12 children. A mole is just 6.022 times 10 to the 23rd, whatever. So I could have a planet made out of 6.022 times 10 to the 23rd donuts. Because that's probably a very large number, and it would probably be a planet-size amount of donuts. If we took a mole of oxygen atoms, that's 6.022 times 10 to the 23rd oxygen atoms. It's just a unit conversion, essentially. Converting this number of whatever into a mole. Let's keep moving on. Oh, perfect. This video is going to, it's really quick, but it explains what I'm trying to say, and it gives some good visual aids. If you are not yet understanding what a mole is, please, please, please watch it once or twice. I think it does a very, very good job at defining what a mole is. Alright, so if you have watched that video now, we're going to go through the math a little bit. So 1 mole of carbon, right? How many atoms of carbon is that? Well, this is just a mole, right? So it will always be 6.022 times 10 to the 23rd whatever. And we're talking about carbon atoms. So this will be 6.022 times 10 to the 23rd carbon atoms. Okay? Because 1 mole is always this number. Now, here's the cool part, and we're going to do another little bit of reach around like we did for the SI units. We're going to connect here to a previous unit. So, 1 mole of carbon, right, that's 6.022 times 10 to the 23rd carbon atoms. That number of atoms, okay, 1 mole of atoms, weighs 12 grams. Any idea where 12 comes from when we're talking about carbon? If you look on the periodic table, and I'm sure some of you are already there, the mass of carbon is 12.011. And I should probably change this. Okay, I'm going to put 12.011 grams because it is exact. We define 1 mole of carbon as 12.011 grams. That comes from the periodic table. It turns out Avogadro's number, the mole, works out so that the atomic mass here, okay, the weight, right, AMU, 12.011 AMU, when you scale it up and you take 6.022 times 10 to the 23rd atoms, if you have 1 mole of carbon, it actually works out so that it becomes that number in grams. So any number on the periodic table is just that heavy in grams once you have 1 mole of it. So let's do lithium here, okay? 6.94 is the atomic number. If we had 1 mole of lithium atoms, right? If we had 6.022 times 10 to the 23rd lithium atoms, that would weigh 6.94 grams. Or helium. 1 mole of helium would weigh 4.0026 grams. It's the atomic number moved into grams. So, let's see. Oh, I just kind of gave it away here. But it's the atomic mass is the mass of a single element, okay, and it's converted over to grams. So let's check nitrogen here. 14.007 grams. If we go to the periodic table, hey look, 14.007 AMU is what the atomic mass is. So when we convert it over to our mass here in grams, 1 mole of it, 14.007, boron, okay, same thing, 10.811 grams, whereas boron, 10.81. All right, we did lithium earlier. What about sulfur? I'm going to highlight this for a sec so you have time in the video. Pause here. Okay, what is sulfur? What's the mass in grams? Let's check. Sulfur, 32.06 AMU. 1 mole of sulfur would weigh 32.06 grams. Let's keep going here. We're going to do some more math here. Let's say you have 2 moles of nitrogen. How many nitrogen atoms do you have? I'm going to switch my apps here. I'm going to go over to my drawing board. All right. The mole is like a unit conversion. Okay? So we have to kind of remember back to our 0.6 standard. We have 2 moles of nitrogen atoms. Okay? And we want to convert that over to a number of atoms. So we're in moles trying to get to atoms. So we've got 2 moles of nitrogen. Now, we need to get rid of moles, right? So we're going to divide by 1 mole of nitrogen. So that's going to cancel out moles of nitrogen, but not the numbers, remember. What is 1 mole of nitrogen equal to? Well, 1 mole of anything, right, is 6.022 times 10 to the 23rd. And what are we concerned with? Nitrogen atoms, right? So this is 6.022 times 10 to the 23rd nitrogen atoms. Oops, I don't know why I did a multiplication there. Okay, so if we just did this, right, should be 1.2. And my apologies, I'm just doing this in my head, so if I get it wrong, please don't blame me. So I don't have a calculator app here with me right now. Let me double check. 2, 12, 4, yep. Okay, 1.2044 times 10 to the 24th nitrogen atoms should be in 2 moles. Right, we're just doubling 1 mole's worth. Oops, wrong tab. We're at 12 minutes. Just want to check how we're doing. Okay, let's say we have 3 grams of helium. How many moles of helium atoms is that? All right, let's do this one together. Let me get these numbers. 3 grams helium, and we are converting to moles. Okay. 3 grams of helium converted over to moles. Let's go, eraser. Keep up with me. 3 grams of helium converted to moles. All right, again, we are originally in grams and we are converting to moles. Let's keep that in mind. So 3 grams of helium. Now, the tricky part for a lot of people, right? We have grams. We need to get rid of grams. What do we divide grams by? That's going to be more grams of helium, right? But how do I know how many helium grams? This is where we go back to the periodic table, what we just figured out, right? What is 1 mole equal to? Well, for helium, it's 4.0026, okay? 4.0026, and I'm going to open up another tab here so that we can do this calculation, because I do not have a calculator on me. Okay, so 1 mole is equal to 4.0026 grams, and that is what 1 mole of helium is, right? So we're getting out of grams, and we're getting 2 moles of helium, which is exactly what we wanted, right? Remembering our conversion factors here. So we are free to solve this problem right now. So we're going to take 3, divide it by 4.0026, and we get, just about 0.75. So I'm just going to round that. You can see here 0.7495. Might as well just say 0.75-ish. And that is moles of helium. And this makes sense, right? 3 grams here is about 3/4 of what a mole is. So we have just about 3/4 of a mole of helium. Makes sense to me. Let's keep going. I think I have a few of these problems. Let's say you have 32 grams of magnesium. How many moles of magnesium is that? It's a good question. I don't know. Okay, 32 grams, and we are converting to moles. So let me erase all of this, and we will get there. Okay. If you are working with me, okay, and you feel confident, try this out on your own, and you have time to get started here to pause the video while I am working, and then you can repause and watch me go through it. 32 grams of magnesium, and we are going to moles of magnesium. Going from grams over to moles. 32 grams of magnesium. This problem looks just like the last one, doesn't it? We take 32 grams, and we have to divide that. Ooh, computer. My apologies. I hit that with my finger a little too hard and didn't wait for the pen. Okay, grams of magnesium. We have to figure out how many grams are in a mole to do this conversion. So, magnesium, how many grams are in a mole? 24.305. Perfect. Okay. I'm going to round that to 24.3 because I'm running out of space here. And that is 1 mole's worth of magnesium, isn't it? So, our units cancel here, grams cancel with grams, and we are left with units of mole of magnesium, which is exactly what we want, right, if we refer back to our guide here. So we can solve that problem. 32 divided by 24.3. And again, bear with me because I do not have a calculator right now. 32 divided by 24.3. 1.32. So that is 1.32 in our unit moles of magnesium. And again, we're checking, right? 32 grams is initially larger than 24.3, so it makes sense that our answer would be larger than 1. So we have a little bit more than 1 mole of magnesium. Okay. Our next problem. Okay, this one's a little bit different. We have 3.87 times 10 to the 23rd atoms of arsenic. How many moles of arsenic is that? Okay, we need to think about this one for a second. So 3.87 times 10 to the 23rd. Come on, eraser. 3.87 times 10 to the 23rd. I'm going to double check that because I want to make sure that's correct. No. Okay. 3.87 times 10 raised to the 23rd, and that is atoms of not argon, arsenic. AS 3.87 times 10 to the 23rd. How many moles? Okay, so we are converting to the mole. Okay, let me underline. We have a number of atoms. We're converting to moles. Awesome. We know where to end. So we would write down our number, right? 3.87 times 10 to the 23rd atoms. Okay. Man, what do we do here? So we've got to cancel out atoms, right? So we have a number of atoms here. We know we have to get to moles, so I'm going to put 1 mole here. Now, wait a second. We learned that 1 mole of anything, right, is how many of something? 6.022 times 10 to the 23rd. Okay, so what I'm saying is 6.022 times 10 to the 23rd atoms is equal to a mole. So we put 6.022 times 10 to the 23rd here as our conversion factor, because these two things, 1 mole and 6.022 times 10 to the 23rd atoms, are exactly the same. That's our conversion. So that means atoms are canceled out, and we're left with moles of arsenic, which is, look, just what we want. Excellent. Okay, so when you convert from atoms to moles, divide by the mole. Divide by 6.022 times 10 to the 23rd. All right, this will be 3.87. Let's see. 3.87 times 10 raised to the 23rd divided by, I'm going to put this in parentheses so that it doesn't mess up my calculations, 6.022 times 10 raised to the 23rd. Make sure that you use parentheses as well. That gives us 0.643, looks like. So 0.643 moles of arsenic, which makes sense because this is looking like a little more than half, right? 3.87 is a little more than half of 6.022. So we get a little more than half here, 0.6. All right, last thing I think that we have. Let's say you're in the lab, right, and you weigh out 56 grams of copper. How many atoms of copper are you holding? Right there, 56 grams of copper. This kind of conversion is exactly what I'm going to be asking you to do on Friday, I'm thinking. Or maybe next week, because we have molar mass conversions coming next week. I will decide, okay, but either this week or next week, I'm going to ask you to, again, pick some objects in your house, and you're going to figure out exactly how many atoms you're holding. Crazy. You're going to look at your toothbrush, and you're going to be like, Mom, Dad, I know exactly how many atoms are in my toothbrush. And they'll be like, okay, that's good. Happy for you. Science. Let's see, 56 grams of copper. Let's do this conversion. Wrap up this video. My eraser is being slow. Here we go. 56 grams of Cu. And we are converting to a number of atoms. Okay? Grams to atoms. Excellent. 56 grams of copper. Now, what do we have to do first? Right? If you are given grams, and we already went over this, but you need to find out how much 1 mole of that many grams weighs. So let's find out. We go to copper, 63.546. Okay, 63.546. So 63.546 grams of copper is what we're dividing by, and that is what 1 mole of copper weighs, right? So we got out of grams, and you know what? It's kind of bugging me in the past that I haven't used a different color for the X's because it kind of bleeds over. My apologies. If we're doing this in the future to make it cleaner, I'm going to use blue. Okay, we're still not done though, because moles is not the same thing as atoms. So we need to convert from moles to atoms. So we need to divide by the mole, which cancels out moles. And we know that 1 mole of anything, right, is 6.022 times 10 to the 23rd. And we are looking for atoms. And we can just decide what we want, right? Because a mole is a mole of anything. But we want atoms in this case. So, let's figure out how many atoms. So we're going to take 56 and then divide it by 63.546. And then we're going to multiply it by the mole, by 6.022 times 10 to the 23rd. Okay, let's see if I can remember all that. 56. Come on, Mr. Brewster. 56 divided by 63.546 times 6.022 times 10 raised to the 23rd power. Tell us, Wolfram, how many atoms do we have? We have 5.31 times 10 to the 23rd. Come on, 31 times 10 to the 23rd Cu atoms. Okay, which means, right, if we're comparing these numbers, that we have a little bit less than 1 mole of copper atoms, which makes sense because we have a little bit less than 1 mole when we look at the amount of grams. And we can directly translate between grams to moles to atoms, okay? Now that we have the mole, we know all the time any amount of atoms, any amount of molecules, just from knowing the mass of whatever we're holding, which is going to be awesome, okay? In the future, we're going to be able to use that a lot. Okay, so this is the kind of conversions that I'm asking you. If you are uncomfortable with conversions, right, 0.6, you need to go back and refresh that, okay, because we're going to be doing a lot of unit conversions coming up here. This week, next week, okay, probably most of May is going to be doing math with unit conversions, figuring out in chemical reactions what we're looking at. And I know that math bit sounds kind of boring, so I'm trying to spruce it up a little bit, give you some at-home labs where you are calculating, right, how the quantity of reactants that you would have, and we'll see if we can get some at-home labs where you're figuring out how much of a product you'll be making in a reaction or something like that. So I'm really trying to make this not just a worksheet based and trying to make it chemistry, which I know we're not getting at home right now. So keep up on it, okay? Keep going through the videos. I really appreciate it that you are sticking with me, and know that I'm rooting for you and trying to make this as close to us being in the lab as we can be. All right, until next time, I'll see you guys.